So we are in the week 5 practice assignment session. Let us begin. 3 channel impulse responses are plotted below. Which of the channel impulse responses correspond to the channel with the smallest bandwidth? So you've been given 3 impulse responses. Which of them will correspond to the smallest bandwidth?
Madam, can you explain what is the criteria for smallest bandwidth?
Okay. So when you say that your channel has the smallest bandwidth, how do we relate to the temporal resolution of it? Here, the impulse response has been plotted. The amplitude this is time. So the bandwidth is small. It means it has a larger temporal resolution, or it means a very bad temporal resolution. So which of the impulse response satisfy that criteria?
The black one.
Yeah.
C.
So the answer is C. Time resolution is inversely proportional to the channel bandwidth. When you have less resolution in time, the impulse response looks smooth, like you cannot resolve it in a very fine manner. That's the thing. So the answer is C. Consider a scenario where the receiver is between the transmitter and the reflecting wall, and it's moving towards the reflecting wall. As the receiver is closer to the wall, which of the signals correspond to the resultant wave received by the receiver? So you have a wall, you have a receiver which is moving towards the wall, and then you have a transmitter. Try to get the expression of the received signal at the receiver, or at least what are all the components that will be involved in the received signal. Then I think you might be able to get an idea.
Again, it will be the black one because it is getting modulated by the Doppler frequency, which is much lower in frequency.
Yes, it's the black one. But how can we explain this diagram? Like, if you go to the thing, so I have a signal from the transmitter which is reaching the receiver directly, and there's another signal which is getting reflected from the wall. If you see, for this first signal, the receiver is moving away from the transmitter. So I'm having a Doppler shift that's negative. In the sense, if it could be Fc minus Ft. And then for the second signal, which is getting reflected from the wall, uh, the receiver is actually moving towards the wall. So I'm going to experience a positive Doppler shift. So what we'll be seeing is, at the resultant signal at the receiver, it will be superposition of two signals with Dopplers like this. For a Rayleigh fading channel model, R, which is product of Z into S plus N, where Z is a complex Gaussian random variable with mean 0 and variance 1. What is the probability that the received signal's power is at least 8 dB below the mean power? From the channel model, try to get the expression for received signal power, and then try to find the probability of that power being 8 dB below the mean power. Can we see the solution? Am I audible?
Yes, madam, go ahead.
We have R as Z into S plus N. So how do we write, or how do we get the expression for received signal power? PR will be equal to mod of Z square rho. So this will be expectation of mod of S square divided by expectation of mod of N square. This will be our mean received signal power. So if we have to find the probability of the received power being less than the mean signal power by like at least below 8 dB below the mean power, so it means a signal power minus 8, or we could write it as rho by 10 power 0.8. So probability that mod of Z square rho lesser than rho divided by 10 power 0.8. Now you will get to this expression. If Z is a complex Gaussian random variable, what will be the distribution of mod of Z square? It will be exponential distribution. Since it's 0 mean and variance 1, here it will follow exponential distribution with mean 1. Hence, you could write the expression for exponential distribution and then you could find the answer. In a similar fashion, now if you're considering a flat fading system and this Z is now again a Gaussian random variable with mean 0 and variance 1. If a deep fade occurs when the SNR falls below 0 dB, that is, when norm of Z square rho is lesser than or equal to 1, that's when we are expecting a deep fade. What will be the approximate probability of a deep fade? So basically, what is the probability that mod of Z square rho lesser than or equal to 1? Okay, so it's in a similar fashion. We have to find the probability of deep fade, which is probability of mod of Z square rho lesser than or equal to 1. Same as mod of Z square less than or equal to 1 by rho. We know that it is Gaussian, complex Gaussian, so mod of Z square follows exponential distribution. It's again this almost a similar way what you have to do. And once you get the solution 1 minus e power minus 1 by rho, what you've been asked to do is calculate the approximate probability at high rho. So we're trying to write the expression for this. So it's 1 minus 1 by rho plus, I mean you'll have other terms, 1 by rho plus 1 by rho square minus 1 by rho cube. So those are all higher terms. So since rho is high, all those terms will be neglected and hence you'll have just 1 by rho. How does the Rayleigh factor, the Rice factor k, change with a decrease in the power of line of sight component? So how does k change when there's a decrease in the power of line of sight component? Can somebody tell how do we express or what is expression for k?
Expect a decrease. There's a decrease. Rise factor is equal to power in line of sight by power in divided by power in line of sight.
Yes. So it is going to decrease because they have
Yes.
a direct relationship.
Yes.
So the rise factor is power in line of sight component divided by power in the non-line of sight component. So they both have a direct relationship. If the power in line of sight component decreases, the rise factor is also going to decrease. What is the most appropriate multipath model for cellular transmission where a dominant line of sight plus many weak reflections are present? Which kind of a model can represent this? Like a dominant line of sight plus many weak reflections.
Ricean.
Yes.
Ricean.
The answer is Ricean fading. Actually, to some extent, we could tell Nakagami distribution also, where close to their means, Nakagami distribution is a good approximation to the Ricean distribution. However, their tails vary significantly. So the answer here is Ricean fading.
And Rayleigh fading is a non-line of sight.
Yes, yes. Multiple individual reflections. Like you don't have a particular dominant reflection that's coming. There's no line of sight component. Okay. Consider the graph given below. What is the fading margin for a rise distribution with k equal to 0.3 dB such that the outage probability is less than 5%? So from this graph, what is your fading margin? If you see KR as 0.3 dB, so the fading margin is minus 11.5 dB. Which of the following can result in catastrophic error propagation? Coherent modulation and coherent detection, differential modulation and differential detection and coherent modulation, or coherent detection and differential modulation. Which of the following result in catastrophic error propagation? That is, one error will lead to the next and lead to finally all the following things will become erroneous.
Just made a notes.
Okay.
My notes is wrong.
Okay. Let's see which. When you're doing coherent detection, you will be trying to do channel estimation, and then you'll be doing a tracking, and then you then you will try to decode, and then it will repeat the process. Now, if there's any error in the tracking, actually it is going to affect your further estimation errors also. Basically, your error propagation will be possible here. Same way, when you see differential modulation, your theta k at the present at kth time, how can we write it? Could be theta k minus 1 plus delta theta k. So the information about the current bit will be carried in this delta theta k. So in both these situations, there are possibilities of catastrophic error propagation. Yeah. So coherent detection and differential modulation. If there's an error in detection of one bit because of considering differences, the error will propagate to future bits. Moving on. Which of the following is not a linear modulation technique?
FSK.
Yes. What is a linear modulation technique? Basically, the baseband signal will be linearly related to your modulating signal. If you see OQPSK, it's just offset QPSK, and pi by 4 QPSK is also just you have a pi by 4 phase shift to your QPSK scheme. We know about the BPSK scheme, so the answer is FSK. Here, based on your bit, you'll be modulating with two different frequencies, say F low and F high, something like. Okay. QPSK has dashed the bandwidth efficiency of BPSK.
That's twice.
Yes. So the place where you're going to send one.
Because the 2 bits we send it
Yes.
to PSK.
Right. So the answer is twice. The next question. The error probability of DPSK is dash worse than PSK. The answer is twice. Basically, it's 3 dB. So in PSK, if you see the receiver side decision making side, there will be only one noise term that is involved. But in DPSK, there will be two noise terms that's involved. And finally, the error probability of DPSK will be twice worse than PSK. Which of the following is false for a characteristic of flat fading?
A, nonlinear phase response.
Yes. So the answer is nonlinear phase response. For a non-fading signal component, the small-scale fading envelope distribution will be dash. It's a non-fading signal component. In that situation, the small-scale fading envelope distribution will be dash. Actually, the answer is Ricean fading. I'll tell you how. Here, this component is a non-fading signal component, so we could take it something like a very dominant component. Along with this, you have some small-scale fading envelopes. So the answer is Ricean distribution.
Okay, ma'am.
Okay. When you have frequency selective channels, there is an irreducible BER flow that is created. What do you think is the reason for this? So, in frequency selective channels, because of the multipath delay spread, you will have ISI that is brought in, which you cannot compensate or you cannot do anything with that. So definitely, when you have frequency selective channels, you can expect a BER flooring that's happening. Something like so if I have to plot which is BER versus SNR, we could instead of a curve falling like this, we could expect some kind of a flooring that's happening. This is the characteristic of such channels. Okay. Which is easier to implement and less complex? Which kind of a detection is easier to implement?
Coherent detection.
Okay. Actually, the answer is non-coherent detection because in coherent detection, you need to know the knowledge about the channel. So basically, you should do channel estimation, and you need to know the exact knowledge about the channel to do coherent detection. But to do non-coherent detection, we don't need any knowledge about the channel. So generally, they say that non-coherent detection is easier to implement and it's less complex. Which of the following bandpass modulations has the highest bandwidth efficiency? Okay, I'll give you the idea behind this. Generally, in quantum modulations are said to have the highest bandwidth efficiency, and even among them, higher memory modulations are said to have the maximum bandwidth efficiency. So the answer here is coherent 256 quantum. Trying to find the moment generating function. So try to write the formula for moment generating function and try to solve this. So moment generating function is another way of representing a random variable like probability distribution function and probability density functions. So the special thing about moment generating function. So the moment generating function is used to find the moments. Yeah. So the formula is like this: integral x1 to x2 e power tx f of x dx. So f of x is given, x1, x2 is given. So substitute, you get the answer. It's e power 2t minus e power minus 2t by 4t. GMSK is a dash of MSK. The answer is derivative. So it's like to limit the bandwidth of MSK, you pass it through a low pass filter whose impulse response is Gaussian shaped. So it gives a Gaussian response to an impulse, and hence it's called as GMSK. Thank you.